Okay, Chapter 3, Day 7, Optimization. You guys have all of these on the worksheet that I handed out to you. So, optimization is the process of finding maximum and minimum values in applied problems. So, what does that mean? Real world examples. When would you use this in real life? Here you go. Alright, so again, on the worksheet, the guidelines, and I'll refer to these as we're solving the problems. Draw and label the situation, identify information, and I'll talk about them as we're working through an example. What is the smallest perimeter possible for a rectangle whose area is 16 square inches? Okay, so we have length times width. So we know the area of the rectangle is 16 square inches. Alright, determine the third step. Determine the equation to be optimized. Optimization is a max or a min. So we're attempting to find the smallest perimeter possible. So perimeter of a rectangle is twice the sum of the length and the width. Using the given information, write the equation in terms of one variable. So the given information is the fact that the area is 16 square inches. How do you find the area of a rectangle? Length times width. So using the given information, solve for one of the variables. So let's solve for L. Write the equation to be optimized in terms of one of the variables. So into my perimeter equation, I'm going to replace L. I'm going to distribute the 2, and I'm going to replace L with 16 over W. Okay, so now my optimization equation is strictly in terms of W. So I multiplied 2 and 16, rewrote W to use the power rule. Alright, find the derivative of the optimization equation. So the derivative of P, negative 32, W to the negative 2, plus 2. Find the critical numbers of the equation. So where does my derivative equal 0? Okay, so I get 2 equals 32 over W squared. I get 2W squared equals 32. Dividing by 2, W would be plus or minus 4. And then it says determine any endpoints if applicable. Alright, we're talking about perimeter here. So when I look at my domain of this function, I know that my dimensions have to be bigger than 0. Okay, now we get another critical value. Where does the derivative not exist when W equals 0? So on our number line, we'll put a soft bracket at 0, and the only critical value we're concerned with is 4. Using the first or second derivative test, determine the existence of a max or min. So I'll use my first derivative test. Any number between 0 and 4, if I plug that into my derivative, I get a negative value. Any number bigger than 4, I would get a positive value for my derivative. Therefore, W equals 4 is a minimum. Okay, so the final step actually answer the question. So what's the smallest perimeter possible? If the width of the rectangle would be 4, go back to the given information to solve for the missing variable. So 16 equals L times 4. So my length would be 4 as well. And then to answer the question, what's my perimeter? 2 times the sum of the side lengths. So the smallest perimeter would be 16 inches as well. Okay, so the steps. This would be steps 1 and 2. Step 3, determine the equation to be optimized. Okay, this would be like 3A and B. Using the given information, substitute that information so that the optimizing equation is in terms of one variable. Find the derivative of the optimization equation, so using the power rule. Find the critical numbers, that would be your 5th step. Okay, we found part A where the derivative is 0, and then B of that where the derivative doesn't exist, taking into account any restrictions on the variables. Use the first or second derivative test to actually determine a max or min, and this is where most students, you forget to do this. When you only find one critical value, we sort of assume that that would be the minimum. This step is most important when you find more than one critical value. And then lastly, actually answer the question. So it didn't ask for the dimensions, it asked for the smallest perimeter. So 16 inches would be our final answer. Okay, I believe this is number 22 in your textbook. A rancher has 400 feet of fencing with which to enclose 2 adjacent rectangular corrals as shown. What dimensions should be used so that the enclosed area will be a maximum? So we're looking to maximize the area. Okay, now this gets a little bit tricky. The area of this, so we have 2 adjacent corrals, X, X, and Y. So the area would be X times Y plus another X times Y. So the area would be 2X times Y. All right, we have to take into account this fence here as well with the given information. So the rancher has 400 feet of fencing. So if I'm talking about fence around each corral, that would be my perimeter. So my perimeter, I have 4 X's and 3 Y's. Using the given information, solve for one of the variables from the perimeter equation. So if we solve for X, 4X equals 400 minus 3Y. Divide by 4. Now take this value for X and substitute it into the area equation. So 100 minus 3/4 Y times Y. Alright, and we want to write this, I'm going to multiply by 2 and I'm going to distribute the Y. So I just have the sum of 2 terms. So I get 200Y minus, this would give me 3/2 Y squared. Okay, so distributing the 2 would give me 3/2 Y and then multiplying by the Y again. Right, so area is 200Y minus 3/2 Y squared. Okay, so find the derivative of this equation. 200 minus 3Y. Find the critical numbers. 200 equals 3Y. So 200 divided by 3 would be Y. We're talking about dimensions for area here. So again, when I look at my number line, I can't have any values less than 0. If I plug in any number between, let's plug in 1, we know that's nice and simple, that'll give us a positive value. If I plug in 100 here, I would get 200 minus 300, so that would give me a negative. Okay, the question asks, we wanted the area to be a maximum, therefore 200 thirds is a max, because the derivative switches from positive to negative. Okay, because we did the second derivative test, let me just show you how that works. If I took the second derivative of the function, the second derivative is just simply -3. Therefore, the second derivative at any critical number is less than 0. And we know if the second derivative is negative, function is concave down, so this value would be a maximum. So this is your first derivative test or your second derivative test. You only have to use one of them. Alright, now let's answer the question. So the question was, what dimensions would maximize the area? So we go back to our area equation we determined was 2x times y. And our given information, we know our perimeter of 4x plus 3y was equal to 400. So now that we have a value for y, we're going to plug that into the given to solve for x. So 4x equals subtracting 200 from both sides, so x would equal 50. So what dimensions would maximize the area? A pen of, 50 feet by 200 thirds feet. Now if the question asked, and it doesn't, what is the maximum area, then you would plug these dimensions into the equation 2x times y. Okay, last example. Which point on the graph of y equals square root of 16 minus x squared is closest to this point? Okay, so closest to the point, we're looking to minimize the distance between the 2 points. So this is our distance formula. Our given information is exactly this, okay? We know that the point 1 square root of 3 is on the graph of this function. 15. Okay. Disregard that. That's not true. Okay, the domain of this function, you can verify that the domain of this is from -4 to 4, so that'll be important when we go to actually find the minimum. Okay, so now let's work with this. We know that, so this is our given information. Okay, we do have two pieces of information that we can use in our distance formula. So our distance formula, what's the difference in the x's? So I'm looking for the x coordinate of the point closest to this one, -1. Now my y value, I can rewrite y to be in terms of x. So y is equal to 16, square root of 16 minus x squared. Then I'm going to subtract the y coordinate of the given point. Okay, now trust me here. Let's look at this real quickly. The distance is closest when what's underneath the radical is a minimum. So I really only need to focus on the function underneath the radical. We can totally disregard that it's the square root. Okay, so trust me on this one, and it'll make our derivative a lot simpler. So this is our equation to minimize. Okay, so then let's continue the steps. Find the derivative. So first I'm going to expand this as much as possible. So expanding a binomial, square the first term, double the product of the two terms, square the last term. Using that same reasoning, square the first term, double the product of the two terms. Alright, when I'm multiplying two radicals, I can multiply what's underneath. So I get 48 minus 3x squared. Square the last term. Alright, combining some stuff. My derivative is -2x minus 2 times the square root of 48 minus 3x squared, and then 3 plus 1 gives me 4. Okay, in the interest of time, we'll finish this problem in class, but for homework, do what's on the sheet that I handed out to you. Pages 223 to 224, numbers 4, 8, and 21. Okay, the problems on the back of the worksheet we'll work on in class. So again, don't finish this. We'll do it in class and have these prepared.